All right. Well, there's no one here yet, so I guess I'll go ahead and get started. We are finishing up chapter 24. I have a few more examples related to capacitors that we need to get out of the way. Of course, we have a test uh, a week from yesterday, or excuse me, for you guys, this is online. It'll be next week. You have a test that is supposed to be done by Monday of the following week. So I wanted to make sure we finish off all the type of examples I'd like y'all to be able to uh, see before you do your homeworks for chapter 24, as well as before you take your tests for chapter 24. That includes both the online test and the face-to-face test, both of which are supposed to be done next week slash the following Monday for my online classes. So, anyways, let's go ahead and get started with that. I'm going to start by opening up my iPad and sharing the screen with you. I have three examples on there, and we probably going to do a little bit more than that, but we'll just start off with those three to begin with. So let me go ahead and share my iPad screen. It should come up any minute now. Still waiting, folks. Still waiting. Don't know why it's going so slow. There you go. That should pop up any second now. All right, so there it is. I think, yeah, this is it. Oh, we have a student arrived. Right. Hey Jennifer, glad you could make it. I was just getting ready to start my first example. Then I realized I need a blank page before this. So I am going to put a blank page before this real quickly. And before paste page. So we have a few things to talk about regarding capacitors. Hopefully you've been keeping up with the videos. I know you haven't been able to be here a couple times. Again, that's not a judgment or anything. Not a judgment or anything. I told everybody y'all are welcome to come anytime. And also, there's been a problem. The video I did on the 25th has not been posted yet. I had to do some editing, and I'm missing some stuff on that. I should be able to post that tonight, though. But either way, we'll go ahead and post it, and we're going to start off with that. What I need to do before this, though, is I wanted to discuss a little bit more about the fundamental ideas behind capacitors, one of which is what happens when you put a dielectric in there, not necessarily the description at the molecular level, which we'll talk about hopefully today as well, but specifically just what happens to capacitance. And then two, there's a neat little uh, derivation that you can do using what we know about capacitors, and later we'll be able to do the same thing using what we know about inductors. But the calculation ends up giving us a result that's very useful, and not only that, it turns out to be the actual generic correct result, even though we happen to make it up based on a capacitor in this case and an inductor in the other case. So let me start off by first reminding you that we have a certain amount of energy associated with a charged capacitor. So to do that, what I want you to recall is we found that delta U is equal to Q times delta V. We can actually make that into a differential by saying something along the lines that U is going to equal to some amount of work, and that amount of work could equal to the integral of Q dV. So I'm just going through work as one of the ways because we know that potential energy can be, in fact, derived as a result of a work calculation. So that's why I touched base with W in there instead of just calling it U from the get-go. Now, what we do know is that C, the capacitance, is defined to be the charge per unit voltage. And because of that, we know that Q, which if I switch to lowercase, that'll become Q, is equal to C times V. So we can actually put in here CV dV, and C, of course, is the capacitance of a particular capacitor, and that we know is a sort of a geometric quantity that doesn't change. So in some sense, it's a constant, and therefore this integral just becomes 1 half CV squared. Obviously, it's plus a constant, but we're allowed to take any potential energy and add an arbitrary constant, and it'll still be the same potential energy with no problems. So what we just did was derive a formula for the potential energy, or for the energy stored in a capacitor, which we might choose to think of as potential energy. And this is the version of the formula that I most like because it's reminiscent of 1 half K x squared, and it's even a little bit reminiscent of 1 half M V squared. That's sort of the relevant part here. And now that I have that, I can go ahead and use U is equal to 1 half CV squared as one of them. But that's the one that you want to use if you have the capacitance and the voltage. But what if you don't have the capacitance? What if, for instance, you have the charge and the voltage and you want to know how much energy is stored there? Well, if you don't have the capacitance, then you can replace the capacitance with Q over V. So that would become 1 half Q over V times V squared, which is just 1 half Q V. So that's another version. Additionally, we might wish to do it without voltage. So, for instance, if we didn't know the voltage, we could actually replace the voltage with Q over C, in which case we'd get Q squared over C times 1 half. These are the three formulas. I already gave them. I think I might have even derived it earlier with Josh was in here, but I just wanted to make sure y'all knew exactly where that came from or whatever. And this is the energy stored in a capacitor. You should be able to work out that in your own practice that the units do work out to be joules. Remember, the unit for the capacitance is a farad, and a farad is defined to be coulombs per volt. Excuse me. And a farad's considered to be a coulomb per volt, and that volts are actually considered to be joules per coulomb. That should be enough for you to figure that out. Now that we have that, I want to do a neat little calculation. Let's calculate the energy stored in a capacitor, and I have no idea why I'm writing in red there, but the energy stored in a capacitor we know is given by 1 half C V squared. So here's the case where I'm going to do a derivation based on the idea of a parallel plate capacitor, and it's going to give me a result. And in fact, that result's going to turn out to be the perfect result, the exact result that you would get if you did a more complete study in general of the energy stored in an electric field. So I'm going to start off by doing nothing with the 1 half, of course, but using the formula for a parallel plate capacitor in a vacuum or even in air to some extent because the epsilon zero is so close to epsilon for air. So it's epsilon zero A over D is the capacitance. Now, the other thing we learned is that we take the integral, negative integral at E dot dl, and that allows us to calculate the voltage from, say, the negative side of the capacitor to the positive side. And what we found was the voltage was actually equal to the electric field times the distance, but that was specifically because the electric field between the plates of a parallel plate capacitor, at least between the plates of a really large parallel plate capacitor with a small gap between them, between the plates, that energy, that electric field was a constant. So when the electric field's constant, we know V is equal to E times D, so we can replace V with E times D. So that's what I'm going to do, E times D. Of course, the voltage was squared, so you can see that's going to be E times D squared. Now we can take the 1 half, we can take the epsilon zero, and what we're going to have is A over D times E squared times D squared, and you'll see that this exponent of 2 will cancel out with the denominator D, and now we have left, oops, now we have left 1 half epsilon 0 E squared times A times D. Now, if you look at a parallel plate capacitor, and I'll try to draw one that has a big gap between it just to make it a little obvious what I'm seeing here. But let's say our parallel plate capacitor is something like this, and you know, for instance, that the area of the parallel plate capacitor, the area of the individual plate is A, and the separation distance is D. So perhaps you can look at this diagram and figure out what A times D would be. Jennifer, do you think you might know what A times D would be for that particular parallel plate capacitor?
No, I'm still writing.
No problem. Uh, if you look at it, it's actually the area multiplied by D. So it turns out to be the actual volume between the plates. So that's the volume between the plates. And if you remember, from either doing the electric field mapping or whatever, you probably remember that the electric field falls off really quickly when you get outside the plates. So the strongest part of the electric field is definitely between the plates, and it's fairly uniform. And the electric field gets quite a bit weaker outside of the plates. So it might be reasonable to think that the A times D is the vast majority of the volume of the electric field established by the capacitor. So we can turn to something called the energy density, and the energy density is the energy per unit volume. So the energy density, we're going to write it as a lowercase u, and it's technically defined to be the uppercase U divided by the volume. And in this case, we know the volume was A times D. So if we divide out A times D from that expression, we'd get 1/2 epsilon 0 E squared, and that turns out to be the right answer. That is exactly the energy stored in the electric field. Okay, so that's another important result that I wanted you to get, and it's really nice because we can do it with a parallel plate capacitor, get the result, and turn out to have that result to be exactly the right one. This will come in handy as well later when we're starting to try to see the connection between electric fields and magnetic fields, because it turns out there's an exactly similar expression when we get into magnetism that basically says the energy density is 1/2 1 over mu 0 times, instead of E, the magnet of the electric field squared, it's going to be B, the electric field squared. So you can see exactly how these formulas relate, and you can even see sort of somewhat of the relationship of epsilon 0 versus mu 0 in that they're sort of reciprocal quantities in some sense, which you really won't understand for some time. But anyways, the main thing is I wanted to express that to you. Now, the one last thing that I wanted to express to you about a capacitor is, in general, you can take a capacitor and you can fill the space between the positive plate and the negative plate, no matter what kind of capacitor it is. You can fill the area between the plates, or the volumes between the plates, with a dielectric. Now, a dielectric is a fancy word for a non-conductor or for an insulator. So this is what the word I'm saying is, and there's a constant associated with it called the dielectric constant, and that dielectric constant is given the symbol K. I remember using kappa, so it might have been kappa at one point, or it might have just been all this time I've been thinking that K was a kappa. But anyways, in this book we're definitely using K. Now, if you actually take a capacitor and make it identical to a capacitor that just has air in it, but this time you fill the space between the plates with a dielectric of a constant K, then that makes your capacitance become C equals K times C0, where C0 is the capacitance without the dielectric. So by just adding a dielectric between the plates, you increase the capacitance from C0 to K times C0. And your book is nice in that it comes with a table of dielectric constants in it. And just to give you a couple of examples of exactly what the dielectric constants were, I'll read off a couple of them. You can see them. They're on, I can't even remember the page number because we use ebook so much. 704 is the page number. But for instance, air has essentially a dielectric constant equal to 1, which is really what a vacuum is. But it turns out if you really, are doing some high precision stuff where you've got multiple decimal places that you can study. It turns out in the fourth decimal place, there's a 6. So you can go 1.0006 is the dielectric constant of air. So I could write K air is equal to 1.0006. Again, this is from page 704 of Giancoli. Giancoli's Physics for Scientists and Engineers. They normally abbreviate it PSEG, and it's the fifth edition. So just in case anybody's wondering, that's what we're talking about. So the dielectric constant for air is obviously 1.0006. The dielectric constant for a vacuum is just 1. For paraffin wax, for instance, you can see that that would be 2.2 for polystyrene, which I suspect you have some idea roughly what that is. The polystyrene has a dielectric constant of 2.6. If you put some kind of vinyl or plastic, it can be a dielectric between 2 and 4. You can put paper, that's 3.7. You can put quartz, that's 4.3. Oil is 4. Glass, Pyrex is 5. Rubber or neoprene 6.7. So pretty cool stuff like that. But the other advantage that this dielectric gives you is if you remember when we first started talking about capacitance in chapter 24, we said you could imagine a really big sheet that you could use. Maybe it's made out of mylar or something metallic, a big sheet, and that would represent one of the plates. And if you put another big sheet next to it, that'd be a problem because the sheets are soft and they can sort of do all this sort of stuff and they could touch each other, and that would sort of make it no longer a capacitor, just a wire shaped really funny. So it's really problematic having air between the plates of a parallel plate capacitor, especially when you want the capacitance to be as big as possible. And we know that for parallel plate capacitors, the capacitance and the area are thumbs up, thumbs up. So if you double the area, you're going to double the capacitance. If you triple the area, you're going to triple the capacitance. And not only that, the capacitance of a parallel plate capacitor is C equals epsilon 0 A over D. That means C and D are thumbs up, thumbs down. So if you end up doubling the distance of separation between the plates, you cut the capacitor down by a factor of 2. So all of that tells us that one, we want the area large if we want a large capacitance, and two, we want the distance between them small if we want a large capacitance. And that all tells us that, wow, these two plates are going to be so close to each other. That could really lead to a problem because we already learned earlier that a electric field of 3 million volts per meter is enough to actually cause air to become a conductor. So if you got an electric field between the two plates that's 3 million volts per meter, then even if the plates were separated by a meter, you would still have the capacitor failing because the air between them would actually ionize and become a conductor. So one of the other things that the table gives you is the dielectric strength of the material. Again, that's the strength of the electric field that would cause the material to become a conductor. And for instance, for air, I already told you it's 3 million volts per meter, and the table says that. But for paraffin wax, you can get it up to 10 million volts per meter. Polystyrene, you can do 24. Vinyl and plastic gives you 50 million. Quartz gives you 8 million, oil gives you 12 million, glass 14 million. You can use mica, and that's 120 million, or water, and that's liquid water, that is, that's 70 million. And strontium titanate is a really great complicated chemical that you could use for a dielectric, and that doesn't do that big a deal in terms of the breakdown strength. It only brings it up to 8 million volts per meter for the electric field strength to ionize it, but it brings in a dielectric constant of 300. So you could literally increase the capacitance of a capacitor by a factor of 300 using that. So that's another big thing we're going to make use of. Not only that, there's a couple of different ways we can do it. We can say C zero would be equal to epsilon zero A over D. That's what we found for parallel plate capacitors. But when you fill that space between the plates with a dielectric of constant K, then it becomes C is equal to K epsilon zero A over D. Now, that's fine, and that's one of the many ways we do it, but a lot of times we choose to uh, think about the material as having its own permittivity. Uh, so if that's the case, then what we'll do is we take the K times epsilon zero and we call that just plain epsilon. So the permittivity of free space, which we've been using 8.854 times 10 to the negative 12th Coulomb squared per Newton meter squared, uh, that's what it is for a vacuum. For air, it's slightly different, but really, really close. But for a particular dielectric material, we can just use plain epsilon, and the result would be epsilon A over D. So that's another new principle about capacitors that we need to know. So that's why I wanted to go ahead and show you that and give you some examples. Now that we have that, I'm going to do some examples to help you better understand how to use this type of information. So let's turn to an example. It says an air-filled parallel plate capacitor has a capacitance of C0, and when its plates are separated by a distance D and connected to a voltage V0, causing it to receive a charge Q0. Uh, okay. Sorry, I realized I got in the middle of that sentence and changed my mind and ended up not making it as complete as it should be. It should be saying an air-filled parallel plate capacitor has a capacitance of C0, and when its plates are separated by a distance D and connected to a voltage V0, it receives a charge of Q0. So I was using a whole different sentence earlier when I was using when I had the word cause in it. So let's just kill that. While it remains connected to a battery, a dielectric with K equal to 4.00 that fills the space between the plates is carefully inserted into capacitor. What will happen to the charge? So this is not a difficult problem, but it is a good problem because you just need to see how the units work out, how the equation works out, all that good stuff. What we do know is C is equal to Q over V. We also know that or C is defined as Q over V. But we also know that C for a parallel plate capacitor is epsilon zero A over D. In this case, we're calling that C0, so I'll just put a C0 on it to make it for this particular problem. And we'll also say that C, when you have a capacitance in there, or excuse me, a dielectric in there, is K epsilon zero A over D. So that's what we'll be using here. And they want to know, while it remains connected to a battery, a dielectric K equal 4.00 that fills the space between the plates is carefully inserted into the capacitor. What will happen to the charge? So what I want you to understand is since it's connected to a battery, then charge can move back and forth between the battery and the capacitor when you do things to the capacitor. Like I could hold the capacitor, the two plates of the capacitor next to each other and then pull them apart or push them closer together. I could do all this kind of stuff. And when I do that, if it's still connected to a battery, then the wires could transport charges down back to the battery or from the battery to the parallel plate capacitor. So charge can change, but the voltage is going to be locked down. So I'll write while the battery is connected to the capacitor. Oops. And that's what we often call it. In practice, you just call it a cap. While it's connected to the cap, the voltage across the cap will not change. So that's another physical fact that we want to put in our brain and keep it alive. Alternatively, another thing you might want to realize, because we did this in the previous example, but I'm restating it now, if you didn't leave the battery connected, then what you've done is isolated the charges on the plate so they have no freedom to move around. So in that case, the charge stays the same, but the voltage can change. So I'll write that down here, even though it's not relevant to this particular problem. However, if the battery is disconnected, then the charges have no way to leave, and the charge on the cap cannot change. So in this case, it's just that first part that's relevant, but the second part I just want to put there specifically because you weren't here last time, and I just want to make sure I reiterate it with any student. So now that we look at that, I'm going to show you the sort of trick that I use in sorting this stuff out. What we know is that C is equal to Q over V, and we know that C went from C0 to C equals K times C0. So uh, we know, looking at these two relationships, that C went up by a factor of K. And we know the voltage can't change. Because of that, we can look at the C equals Q over V and realize that Q must go from Q0, which we assume that was the charge it initially had, it must go to Q, which is actually equal to K times Q0. Did you see how I made that leap, Jennifer? Hmm. Okay. Yeah, it's one of those things that it's so obvious when you look at the equation that you think maybe you're not understanding it, but then you look at it like, oh, well, yeah, obviously, if the V can't change since C has to be Q over V, the Q must go by a factor of K up, and that would account for the C going up. So in this case, they want to know what will happen to the charge. Well, what happens to the charge is that the charge will go from Q0 to K times Q0. And that's it. That's the answer. Any questions on that? All right. Now let's try another example. It says if the air-filled capacitor C0 from the previous example is charged Q0 and then disconnected from the battery V0 and the same dielectric is inserted, what will happen to Q, C, and V? Okay, notice this time they said the battery is disconnected. So I'm going to underline that. Disconnected from the battery. So this means, as far as our solution goes, we're going to make use of C equals Q over V. C0 equals epsilon 0 A over D. C is equal to K times C0, which equals K times epsilon 0 A over D. And we're also going to make use of the fact that since the battery, oops, I left off part of my Y there. Since the battery is disconnected, the charge cannot change. So we know Q and Q0 are going to be the same thing here. That's what we know for sure. So first off, let's talk about charge. So charge Q0 and Q are the same because the battery has been disconnected. Okay. Now we want to try the capacitance. Well, the capacitance, that's going to go from C0 to C is equal to K times C0. That we know is going to have to happen. So I will write that here. And I should make it obvious that that is a subscript 0 there. The capacitance C0 goes to K times C0. That's another answer. And then we also need to know what's going to happen with the voltage. And in this case, the voltage can actually change because the battery was not left connected. And C equals Q over V is what we had for the initial capacitance. So I'm going to write that as C0 equals Q0 over V0. But C0 is going to go to K times C0. So you've got to figure out what could possibly be absorbed there, or which term on C0 equals Q0 over V0. In the general sense, C equals Q over V. What can actually account for that K that is multiplying by the C? You either have to have the Q increase by a factor of K, but we just said the Q can't change, or you have to have the V0 change. And if we did, we'd want the V0 to change so that the K would become part of the numerator. So in order to do that, that means, therefore, V0 is going to go to V0 over K is equal to the new V. So that's what actually happens, and that's the answer to this. Does that make sense? Okay. So what we've learned is that when you leave a battery connected to a capacitor, then the voltage has to stay the same, but the charge can move back and forth. And that actually causes the charge to go up when you insert a dielectric in it. However, when you insert a dielectric in a capacitor while the battery is disconnected, then the voltage is free to change, but the charge cannot change. So in that case, when the battery is disconnected, if we slip a K dielectric in between the plates, then that's going to actually cause the voltage to go down by a factor of K. Okay. Now that might not physically seem that obvious, but when we show you molecular description of dielectrics, that'll give you a little bit better of a model to think about. Right now, what you just want to do is either memorize the thought process that went into this, using the C equals Q over V, using the reasoning for the V staying the same when you keep a battery connected, and using the reasoning for the Q changing when you don't leave one. You can come up with V going down when you insert a dielectric and Q going up when you insert a dielectric. Does that make sense? All right, so there's the second example I had for you, and I just wanted to make sure we were all on the same page with that. And your book does this nice little sentence. I've highlighted it in my copy of the book, and I share that highlight so you guys are supposed to see it. But I think it's at the top of page 706, there's a sentence that says the electric field in a dielectric is reduced by a factor equal to the dielectric constant, but the field in a dielectric or insulator is not reduced all the way to zero as in a conductor. Equation 2410, this is what we're talking about here. It turns out that we can understand the electric field going down, or excuse me, the voltage going down, because what's going to happen is when we add a dielectric, the electric field will go down. So, what they're referring to is this little sentence, or structure of equations, if you will. The E with a dielectric is still equal to V over D. Remember, I told you earlier that delta V equals the negative integral E dot dl gave us that the voltage across a capacitor is equal to the electric field strength times the separation between the plates. So if you just solve for E, you'd see that E is always the voltage divided by the distance in a dielectric, or excuse me, in a capacitor. So what we're claiming now is in a capacitor, uh, when you have a dielectric, you still have the electric field being V over D, but now what's going to happen is that V happens to be the V that we just found, which is V0 over K times D. And the way we interpret that is, and remember those three dots mean therefore. So therefore, we're going to make the conclusion that the electric field in a dielectric is equal to the electric field that it had without the dielectric divided by K. And as I said, this equation is valid inside a dielectric, even if the dielectric's thickness is smaller than the gap between the plates. So this guy right here, this equation is true for the electric field in a dielectric, even when the dielectric does not fill the volume between the plates. Okay. Now, again, that's specifically saying that only about the dielectric part. It's not saying the electric field outside of the dielectric is reduced by a factor of K2. It's just saying only the electric field within the dielectric is reduced by a factor of K. So hopefully that makes it a little more clear. Now that we have that, and by the way, that sentence I was telling you about, that wasn't the sentence I was thinking of, so that might have sounded a little goofy. I noticed it at the end that I was like, oh, this is not the sentence I meant. I think the sentence I was remembering, to be honest with you, I was reading the fourth edition earlier today, and forgetting the slight differences between the fourth and fifth edition, and I think that's what happened. I think I was remembering a sentence that's been removed since the fourth edition. But anyways, not that it was a bad sentence. I'm sure nothing's been disproven about it, but it gave you a nice experimental result, and I thought that's what it was going to be. So I apologize for getting you so excited about that sentence. It didn't matter too much. The big part that did matter was the second part of the sentence, which is what I just wrote down. So hopefully that's good enough. And this is supposed to be an I, not an E. Let me fill in that I.